This is joint work with Pedro Moreno Sanchez and Aniket Kate from Purdue University, as well as Ian Goldberg from University of Waterloo. And talking about Ian, he told me to say hi to everyone he knows. But since Ian tends to know like essentially everyone, I thought it was more efficient to just make a broadcast and also more privacy preserving because you don't have to reveal that you know Ian. And that's a lot about what this talk is going to be about. How do we improve efficiency and privacy? And our key motivation is very similar to the previous talk, so I'm just going to add some numbers here with regard to the lack of scalability of blockchains and in particular Bitcoin. So Bitcoin at the moment manages about 7 transactions per second, while on the other hand, for example, the Visa network manages close to 60,000 transactions per second. So if we're considering to use something like Bitcoin or a similar blockchain-based transaction system as a global transaction system, we do not have the necessary throughput at the moment to manage that. And what would be a solution to do this? Well, one aspect that recently came up was the concept of payment channels. In a nutshell, if you have a payment channel, you have two users, A and B, and they agree upon a local channel that has a certain total capacity X plus Y. And they divide this capacity in two parts, in two balances, namely A can send up to X, for example, Bitcoins to B, and B can send up to Y Bitcoins to A. And now if this is actually used by the two parties, for example, if A sends Z Bitcoins to B, then the balances change in the payment channel. So Z has to be less than X, and the new balance between A to B is X minus Z, and the new balance from A to B is Y plus Z. So this is in a nutshell, the concept of payment channels. What type of systems might make use of similar concepts? Well, the first thing that comes to mind is the Lightning Network. The Lightning Network is a recent extension of Bitcoin that uses these payment channels to realize off-chain transactions, so transactions that have not to be recorded in the blockchain. And in this manner, you can extend the total number of transactions that are possible in a certain time frame by adding additional transactions that use these kind of payment channels. However, our work is not really specific to Lightning. It can also be used by the Interledger protocol, which is a protocol that allows transactions that are cross-blockchain. So you can have multiple blockchains and transactions between those. And the last type of networks are decentralized credit networks, which are networks that entirely work without a blockchain and only rely on these type of channels. So this is the type of networks that we're interested in, but one aspect that is particularly interesting to this work is what happens if we have a sender S that wants to send a certain amount to a receiver R, and the two do not share a payment channel. Maybe because it's too expensive to set one up, or maybe because it requires a trust relationship. What they can do is then have intermediate nodes, and those intermediate nodes forward the payment. And what will happen in this forwarding is that for the intermediate nodes, their total balance does not change. Like in this example, but the intermediate node still has an incoming balance of 15 and an outgoing balance of 8 in total. However, it's just distributed a bit differently between the links after the actual payment. So this is how PassBased Transaction work, and networks that are based upon this type of transactions are called PassBased Transaction networks. Now, in this case, it looked pretty easy how we actually conduct this transaction. But in practice, there is one important problem, which is routing. And routing in this context means how do we find these transaction paths in a network that has possible hundreds of thousand nodes or even millions of nodes? How can you make sure that you find one or several of these paths to forward the payment? And that's the problem that we're addressing in this work. Not so much how do we actually conduct the payment and how do we achieve accountability, mainly for the reason that there's good related work on how to do payments and how you do accountability once you have these paths. So our main problem is how do you actually find those? And in that context, we're considering also the aspect of privacy, because if you're doing a payment in this type of networks, you likely don't want it to be public and readable for everyone that is in the network. So we first define what type of privacy goals should our algorithm have. Then I will introduce you to the key concepts in the design of our routing algorithm. And later, I look into first the privacy analysis and then the performance analysis of this protocol. So let's start with the privacy goals. On a very high level, what we want to hide is the value of the transaction and who's the sender, who's the receiver. Let's make this a bit more specific, but not formal. If you want to have formal definitions, including the respective privacy games, you can look that up in the paper. But the key idea is that one concept that we want is value privacy. Essentially, that means if we have a malicious node in the network, and the malicious node is not involved in the payment, so it's not contained on any of the payment paths, it cannot get any information about the actual transaction value, about how much the sender and the receiver want to send. And the second important concept is sender and receiver privacy. Here the idea is that an adversarial node, even if it is contained on a path, cannot uniquely identify the sender and the receiver. And I should make the point here that what we get is a bit weaker than anonymity in the context of the Tor network, because if you're forwarding a payment, you can still say something like, the sender is roughly in this direction, and the receiver is roughly in this direction. So we don't get quite to the point that we can say the sender could be anyone in the network, but we can obfuscate the sender to the degree that it's not possible for adversarial nodes to uniquely identify sender and receiver of a payment. So how do we do that? Let's start with the setup of our protocol, which is called SpeedyMurmurs. And the main idea is, let's look at this example graph, and let's say these are our payment channels. And to make this a little bit less messy, I did not include the numbers and capacities of the links and represented the channels as bidirectional links. The key idea is that in the first step, we use our favorite distributed spanning tree construction algorithm and figure out a spanning tree of this graph. Then we assign coordinates based on the node's position in the spanning tree. And we decided to use vector-based coordinates. The key idea here is that the root node receives the empty vector as a coordinate, and each node and the other node in the tree receives the parent coordinate concatenated with an enumeration index. So the children of the root node receive the coordinates 1 and 2. The child of the node with the coordinate 1 will get a parent coordinate, which is 1, plus enumeration indices. So it's 1, 1, and 1, 2. And the last node in the graph gets the coordinate 1 to 1. And based on these coordinates, we can then define a distance of 2 coordinates, which is identical to the number of green edges that you have to walk along to get from one node to another. And this can later help us in the routing. There's one more thing. I here displayed the example for like one of those trees, but because it might be a good idea to have multiple payment paths and have combined payments, we do this t times, which is the maximal number of paths you can use to satisfy a payment. Now this is the setup. Now, how does the routing actually work? We have two steps. The first step is the responsibility of the sender. The sender and the receiver have this total transaction value C. However, usually they will not send it along one pass, they will send it along T pass. And what will happen in the first step is that the sender randomly divides the total transaction value C into non-negative shares C1 to CT, and Ci will be the value that is sent using the coordinates that are generated for the i's of these T trees. And then they start the routing, and each node on the path has to decide which of my neighbors do I forward the payment to. So let's see how we do this. Well, each intermediate node will look at its neighbors. It will select a set of neighbors that are closer to the receiver in terms of these coordinates that we defined on the last slide. And it will look at all the links that have at least a balance of Ci. So where the balance is high enough that the sender can actually use the link to forward the payment. So in this example, the node with the coordinate 2 could only forward the payment to the root node because that's the only link that has the necessary balance. And in this way, we then derive these paths between the sender and the receiver that satisfy the necessary payment. And afterwards, whatever algorithm you use to actually settle the payment can be applied to make sure that you can correctly send the money. Now, this is interesting. Why is this privacy preserving with regard to our initial privacy goals? Well, we have a formal proof, but it's somehow intuitively clear that if you're not a node on the path, you remain unaware of the transaction, and in particularly the transaction value C. The more interesting case that we did not really cover in the official definitions is what happens if we have an adversarial node that is contained on the path. In this way, unless the node is contained on all the paths, we can still hide the exact transaction value, but of course it's then possible to make estimations based on the partial values that you see. The second privacy goal that we had was hiding the identity of the sender and the receiver. That looks a bit more complicated because we have this very identifying coordinates. Luckily for us, someone already came across this problem. We already came about this problem in previous work, and we figured out that there is a way to do obfuscated coordinates and hide the sender and receiver on an identity. I'm not going to go into details here because it's previous work. The second aspect is how good is this actually with regard to performance? And performance has two aspects. On the one hand, can we actually discover these payment paths using this algorithm? On the other hand, how efficient is that, or how many messages do we need to figure out what the paths are? So let's first look at the success ratio. And for this purpose, we actually got a real-world data set. So we crawled Ripple, which is a credit network. We got transactions that range from 2013 to 2016. And we got a snapshot of the network that is roughly 60,000 nodes, large with a couple of edges. And we performed simulations on this actual network. The type of algorithms that we evaluated was SilentWhispers, which was the state-of-the-art routing algorithm before we developed SpeedyMurmurs, and also Fort Fulkerson, because you might have realized essentially what we're solving is a flow problem, where the sender is the source and the receiver is the sink. Now, how do we do with regard to the success ratio for transactions that can be satisfied? The Fort Fulkerson's algorithm, it's just by design, can find all of the payment paths, while SpeedyMurmur has a slightly lower performance at roughly 90%. However, you might remember that we had this initial step in the routing where we randomly divided the transaction value onto a path. So if your transaction fails, you can simply redo the step and use a different distribution and try again. And it's significantly better than SilentWhispers, which only had a success ratio of roughly 65%. However, looking at this graph, it seems like we should use Ford Fulkerson, right? Now, remember the start of the presentation where we said we want to have something like a global transaction network. We want to have a high throughput of transactions, which mean that they should create very little overhead. And one way to measure overhead here is how many messages do I actually need to find these paths. Now let's look at this. So this is the 3 categories, and this is my attempt to represent the message count. Try 1. Try 2 looks like this. So Ford Fulkerson needs for one transaction, on average, roughly 50,000 messages. In comparison, our protocol, SpeedyMurmurs, only needs 15 messages. And we're still by a factor of 4 better than the best related work. So summing this up, we presented a highly effective embedding-based routing protocol that I just presented to you. In addition to what I talked about today, we also looked into the issue of how can you dynamically adapt these coordinates when the payment channels change, because you would expect such a network to be pretty dynamic. And also we looked into how do we deal with concurrency in particular, because there will be a lot of parallel transactions at any point in time. And then our evaluation showed that we're effective in terms of having a high success ratio in discovering paths. We're efficient, have in terms of a low number of messages, scalable, and privacy preserving. And the work is, as initially indicated, valid for a lot of different systems, in particular Bitcoin's Lightning networks. And one more note is, if you want to try out different routing algorithms, we already also have all the data sets that we crawled from Ripple and an easy-to-use simulation framework online. And now it's your time to ask questions.
So the first question is in your use for TPAT, which is like the main ingredient they use for privacy. You mentioned that in analyzing it, well, we can assume that as long as the adversary is not a node on the path, then we can prove certain properties or guarantees, which to me seems trivial. The more interesting one would be actually where you have multiple adversaries, perhaps on multiple paths. And so you mentioned that it is impossible to prove based on these partial values. Is that a proof of impossibility, or is it your feeling?
You mean, I mean, we have some guarantees for the sender and receiver privacy, even if the adversary is on the path. For the value privacy, it's a bit more interesting in the sense that, of course, the more interesting case is what happens if the adversary is on the path. Essentially, if the adversary knows some of the values, that will reveal some information about the total transaction value, at least if you use only positive transaction shares. You could consider something like also having negative shares, and that might obfuscate it further. The general idea is how much can the adversary infer having partial transaction values. Well, if they know the initial distribution, how they are generated, they would certainly be able to get a distribution over the most likely transaction value. If they could infer the exact transaction value, generally no, because they cannot know what went on the one path where they did not control a node. Okay, so if I get the question correctly, it was, why do I need to make sure that I have a certain balance with the next node on the path when I'm forwarding the payment? Yeah. So the main idea of these payment channels is that two people agree that they're willing to exchange a certain amount of money. So you might say something like, I'm willing that my best friend, I'm trusting him enough that I will be able to have a negative balance with him of like $100, but I'm not so sure about 1,000. And essentially here the ideas are local agreements that represent the trust or the business relation of the two parties. And essentially it's you're willing to send someone a certain amount, but not more than this. Also because this previous setup, when you created a payment channel, did specify this amount. So it depends a bit on the type of network. Our construction was a bit abstract on the way that it's applicable, as you can see, for multiple networks. If you're thinking about something like Lightning, this total transaction value of the payment channel would be recorded in a blockchain. And if you go below this balance, that would go against the initial recording of what this payment channel is supposed to be like. This is why there are certain bounds on what you can send along the links.